Hey everybody, today we will be jumping into related rates problems. Now I really like these related rates problems because it's a good chance to solve like application-based questions using the tools we've learned throughout the semester. As engineers, pretty much everything you do will be application-based in real world, so it's nice to finally use the math skills you picked up to solve these type of questions. So before jumping into the actual problem, I will say that for any sort of problem you're given that's a related rate, always draw a picture. Um, One, it really lets the grader know kind of like what you're thinking, but also they're very challenging to solve without a picture. Like there's almost every single related rates problem I've ever solved in my years here at UVA, I've always drawn a picture. And then when you get stuck, which you never inevitably will get stuck at some point, the picture often helps you get out of that bind that you're in. So now with this problem specifically, we're gonna is a 10-foot long ladder against a vertical wall. So you have some vertical wall here and a 10-foot long ladder. And the bottom of the ladder is going to slide away from that wall. So I have some ladder right here. And it's going to be sliding away at a rate of 1 feet per second. So that'd be to the right. And we would need to find out in radians per second how fast the angle between the ladder and the ground is changing. So let's define the ground like this. And the angle between the ladder and the ground. So I'm going to write that in as theta. So basically, we're finding the angle's rate of change when the bottom of the ladder is 6 feet from the wall. So for now, just generalizing this problem, I'm going to define this direction as the x direction. Then we also know that the ladder is 10 feet tall. That's a constant value. It's important to remember. Or you can write that down. That is constant. But x here, x is going to be changing. Even though we're solving for it, like the rate of change of the angle at a specific x value, we need to remember that x is going to be changing. And then I'll also write that dx dt is going to be equal to 1 feet per second, or 1 foot per second. That ladder is going to be sliding in that direction at 1 foot per second. So when it comes to this given part, I'm pretty much the value that I'm given is dx dt is equal to 1 foot per second. And the unknown is the rate of change of the angle. So that would be a d theta dt. More specifically, it'd be the rate of change of the angle when x, the distance from the wall, is equal to 6 feet. So our equation. Now, the equation will almost always come from the drawing that you make. I'm pretty sure that my drawing is accurate so far. So let's think about an equation. So we have some angle changing, and we have some floor, or the distance changing between the bottom of the ladder and the wall. So I know we're going to have some x value, and that's adjacent relative to the angle, and we're going to have a constant hypotenuse. So an adjacent value and hypotenuse value, that makes me think cosine. So cosine of theta. And what is that adjacent value? Well, that would just be x. And the hypotenuse value will be 10, because that's a constant. So there we go, that's our equation. Now, it tells you here that we need to differentiate both sides with respect to t. Let's just go ahead and do that. We'll have d dt of cosine theta, and it's going to be equal to derivative with respect to t of x over 10. And you may be looking at this thinking, both of these equations, or both of these functions, cosine theta and x over 10, they're not in terms of t. That's okay though, we can still use the skills we picked up in implicit differentiation to think about how we'll solve that. So first, we're going to solve this derivative in terms of theta. And the derivative of cosine is negative sine theta. And then we're going to multiply by a d theta dt. That's that chain rule portion of implicit differentiation. Same for the right side. Our derivative with respect to x will just be 1 over 10. And then to make it in terms of t, we multiply by a dx dt. All right, I'm looking at this, and this looks pretty good because I have a d theta dt, which is what we're solving for, and dx dt, which is given. And then I also see a sine theta. I'm not exactly sure how we're going to go about that yet, but in the meantime, let's solve for our choice value, our target value of d theta dt. This isn't too bad. We're just going to multiply that negative sine over. Or sorry, we're going to divide by negative sine theta. So we'll have 1 over 10 times dx dt all over negative sine theta. Maybe thinking now, what can we do with this sine theta? Now, sine theta is going to be a constant value because we don't have anything changing with respect to t. So let's go back and draw another little piece of the problem. So I'm going to have this ladder here, and I'm going to have the wall. Oh, that's not very good. And the floor. So we know that the ladder has a length of 10 feet. And then with regards to this problem, we want to find d theta dt when x is equal to 6 feet. So this value is 6 feet. So I have two values, which means you can find a third. And we're going to be looking for sine theta. Right now, I don't have this opposite value. So we need to solve for that. And we can use the Pythagorean theorem. So we will have, or let's just call it h, if you will, like a lowercase h for height. So we'll have h squared plus x squared equal to 10 squared. So h squared is equal to 100 minus 36. H squared is equal to 64. So h is just equal to 8. I'll replace that. And that little h is not to be confused with the hypotenuse value of h. H just represents the height in the context of this problem. Okay, now given this triangle that we have, sine theta will be equal to the opposite. I should also define what theta even is, sorry. Sine theta will be equal to the opposite over the hypotenuse, 8/10. Now that we have this value, we can bring it up here. We also know dx dt from way up here. And now we have values. So let's go down here and solve. We have d theta dt equals 1/10 times dx dt, which is 1, all over, remember that negative sign there, negative 8/10. And then you definitely need to simplify this. We'll have a 1/10 divided by negative 8/10. And then that's not like a division sign, division, which is the same as 1/10 times 10 over negative 8. So our d theta dt will be equal to negative 1/8 radians per second. Units are very important for these problems. Since we're actually dealing with an application now, it's important to know what units we're dealing with and also to put those in the problem. All right, so that is the question there. I hope the solution makes sense. General advice, as I mentioned earlier, always, always, always draw a picture. A lot of times, these related rates problems will be involving some sort of trig or the Pythagorean theorem, so that's definitely something to keep an eye on. In this problem, we use the Pythagorean theorem to solve for a value we needed, but every now and then you could see a Pythagorean theorem question where that's actually part of the equation you're solving. But that wasn't the case now. But there's a chance you'd end up seeing it. In my experience, it's like one that's commonly tested. So knowing trig, knowing Pythagorean theorem, from there, it's just the process. You're going to have a given value and a known value that you're solving for, and then some important equation, and you'll get that equation from your drawing. Drawing. I cannot stress that enough. Putting a good drawing in place will make getting your equation so much easier. And then from there, here you just do calculus. You just use your calculus skills. And then you have to plug in a couple values and you'll come out with a final answer. And with that final answer, you're going to absolutely remember to include units because that's super duper important for these problems. Yeah, well, I hope this helps. If you have any more questions about this, as always, feel free to stop by office hours and let us know.